My name is Tiffany Kataria, and I'm a scientist at the Jet Propulsion Laboratory, California Institute of Technology. At JPL, I'm a scientist there that studies exoplanets, planets that orbit other stars. So my work involves understanding what these atmospheres are made of, what their weather is like, and how we can use telescopes to understand more about their atmospheres. I started on the path to exoplanets and astronomy, planetary science, actually through undergrad. And so, as a high school student, I was always interested in math and in science to a lesser degree. But given my aptitude for math, I actually thought I would go into marketing or business research. But it wasn't actually until I visited Washington, D.C. and went to some of the museums there, the Smithsonian Air and Space Museum in particular, and really saw that there were scientists working on these particular problems. I think that was kind of my aha moment in identifying that that's a career you can pursue. And so from then on, I decided to pursue a career in science. And as I was looking at deciding on disciplines, I had settled on exoplanets after having seen a presentation given by a prominent astronomer at the time, and that really inspired me to pursue then a career in exoplanets. And so really the primary way is via space telescopes like the Hubble Space Telescope, the Spitzer Space Telescope, and this has been largely used to observe transiting exoplanets, planets that orbit our stars along our line of sight. And so we can utilize the geometry of those orbits to leverage the information we can get over the course of its orbit. So when the planet is passing in front of its star, these are typically close-in planets where we're observing the stellar light transmitted through the planet's limb. And so once we subtract off information about the star itself, we're left with information about the planet. So we can learn things like what molecules are in the atmospheres themselves. If we look at different geometries, different wavelengths, we can understand the temperature structure of these atmospheres also as a function of longitude. So that actually starts to tell us something about the 3D structure of these planets and their atmospheres. So the first detection of an exoplanet, an extrasolar planet around a sun-like star, was actually made in 1995 using this radial velocity technique. So this is measuring the gravitational tug between the planet and a star. So that tells you something about how massive the planet is. In this case, these are more Jupiter-like planets in their size and masses. But it wasn't until the early 2000s that scientists were able to detect atmospheres on these planets themselves. The first observation of an atmosphere from an exoplanet was actually made with the Hubble Space Telescope. So that was simply detecting that an atmosphere was there, but then there were larger questions about the temperature structure of the planet. So that was actually made in roughly 2005 by two different teams for two different hot Jupiters, these Jupiter-sized planets that are very close into their stars. And so given how close they are, given how bright the stars were, they were very favorable for these sorts of observations and the first observations of their kind. And so those scientists detected secondary eclipses. So that is when this transiting planet is passing behind the star. So you're actually sensitive to the planet's emitted light. And so that tells you something about the temperature of the planet, so how hot it is. In this case, both of these planets are hot Jupiters. So they're on the order of 1600 to 1800 degrees Fahrenheit, so incredibly hot. And then with Spitzer, the scientists were also able to take phase maps of these planets, so observe the planet from transit to secondary eclipse at these longer wavelengths to then understand what the temperature structure of these planets were like as a function of longitude. So one remarkable thing about these two telescopes that were never designed to observe exoplanets, the Hubble Space Telescope, the Spitzer Space Telescope, is they actually provide a lot of complementarity when it comes to understanding the properties of exoplanet atmospheres. So given that the Hubble Space Telescope operates from ultraviolet wavelengths through to near-infrared wavelengths, you're getting a lot more information about escape processes in the atmosphere. So we've actually discovered for a lot of these hot Jupiter atmospheres, some of even these Neptune atmospheres, that there's hydrogen and helium escaping from these atmospheres at very high rates, and so they're probably losing their atmospheres very rapidly. The Spitzer Space Telescope operates at much longer wavelengths, and so that tells us a lot more about temperature structure, perhaps less about molecules. But the Hubble Space Telescope tells us a lot about the water content in these atmospheres for super Earths down to Jupiter-sized planets and kind of in between. So the discovery of water vapor around an Earth-like planet would tell us a lot about the conditions for whether or not it were habitable. And so that would really be the first step in telling us that surface liquid water might be able to exist on its surface. And so efforts would then follow, I would think, to further characterize, further understand the properties of the atmosphere and its surface. So water is really our best ingredient that we can point to in our understanding of life on Earth and how it's evolved and how it persists. And so when we look at other planets, we're really relying on what we know about Earth's system in understanding the evolution of life and maintenance of life on another planet. And so water is a really critical molecule for all of those processes. Our understanding of Earth's atmosphere can tell us a lot about exoplanets because a lot of these exoplanets are so different from the weather patterns that we see on Earth. So in the case of Earth, Earth is a much faster rotator than a lot of the planets that we've discovered so far, these hot Jupiters. They're much slower rotating, whereas Earth is much faster rotation. And so we expect to see a lot of different cloud bands. A lot of these jet streams that we see on Earth is very much unlike what we see in hot Jupiters and other slowly rotating planets. And so it's really these comparing and contrasting of these atmospheres that lead to a larger understanding of weather, of atmospheric dynamics, and our understanding of fluids on a sphere really in any of these environments.